Welcome to this Explainer. Today, we're going to transform the periodic table from that intimidating, familiar grid of letters and numbers you probably remember into a dynamic, interconnected map of literally the universe's building blocks. We are taking a totally fresh look at the elegant architecture behind this elemental map. Okay, let's dive into our roadmap for today. We'll be breaking this chart down into 5 main regions: decoding the elemental map, exploring the metals and nonmetals, meeting the element families, dissecting the anatomy of a single element, and finally, spotting these elements in our daily lives. Starting off with Section 1, decoding the elemental map. You know, to navigate absolutely any map, you need coordinates. And the periodic table gives us 2 main directions to travel to find exactly what we're looking for. So the absolutely crucial point here is that the vertical columns are called groups, and the horizontal rows are called periods. Why does this actually matter? Well, elements in a vertical group share very similar personalities and chemical properties. Take group 1, for example, the alkali metals like lithium, sodium, and cesium. They are all incredibly reactive, and as you go down that column, their reactivity increases so much that, well, while sodium reacts vigorously with water, dropping cesium into water can actually cause a literal explosion. On the flip side, the horizontal periods really just tell us the row we're currently looking at. The real secret to predicting an element's behavior, that's all about looking at its vertical group. Moving right along to Section 2, metals, nonmetals, and metalloids. Broadly speaking, the periodic table's major territories are split into metals on the left, nonmetals on the right, and a totally fascinating borderland right in between. Notice the stark contrast between these 2 main territories. Over on the left side, we've got the metals. They're fantastic electrical conductors, they can be hammered into malleable sheets and pulled into ductile wires. But most importantly, chemically speaking, metals absolutely love to give away their electrons. Then on the far right, we have the nonmetals. They're basically the exact opposite. They don't conduct electricity well, they're brittle instead of malleable, and rather than generously giving electrons away, they greedily take them from other elements. Why? Just to complete their outer electron shell, which is known as an octet. Now, because of this electron exchange, these elements actually transform. When a generous metal, like sodium in group 1, gives up its single outer electron, it's losing a negative charge. This turns it into a positively charged ion, which we call a cation. Conversely, when a nonmetal on the right side of the map, like fluorine, acquires an electron, it gains a negative charge. It forms a negatively charged ion called an anion. So think of it like this. The left side forms positive cations, and the right side forms negative anions. It is pretty much a perfect chemical match. But wedged directly between these 2 extremes on our map are the metalloids. These are elements like silicon and germanium, and they act as semiconductors. They don't conduct perfectly like metals, but they aren't completely blockades like nonmetals either. And here is a wild fact for you. Their electrical conductivity actually increases as their temperature goes up. If you heat up silicon or shine light on it, it conducts electricity much better. That's the exact opposite of how true metals behave, since metals actually become less conductive when heated. Alright, on to Section 3, meet the element families. Zooming a bit closer into our map, we find that sharing a column really means sharing a family identity, specifically when it comes to chemical reactivity and those all-important valence electrons. This brilliantly illustrates how a group's column number directly corresponds to its outer valence electrons, which entirely dictates the typical ionic charge it'll form. Look at Group 1A, the alkali metals. They have 1 valence electron, so they give it away to form a +1 charge. Group 2A, the alkaline earth metals, have 2 valence electrons, forming a +2 charge. Then, jumping way over to the nonmetals, Group 7A, the halogens like fluorine and chlorine, have 7 valence electrons. They desperately need just 1 more to reach a happy 8, so they take 1, forming a -1 charge. Honestly, the map practically does the math for you. And then, sitting proudly on the far right in Group 8A, we have the noble gases. We're talking helium, neon, argon. They already have their full octet of valence electrons, so they are completely satisfied. As a result, they're chemically inert. They don't want to give electrons, they don't want to take electrons. As our source puts it perfectly, they are completely satisfied and refuse to participate in chemical reactions. Quote, they don't want to do anything, they just want to chill. Kind of relatable, right? Moving to Section 4, Anatomy of an Element. We've looked at the vast regions and the broad families, but now let's knock on the door of a single house on our map. We really need to understand the specific data packed inside just one of these little elemental squares. Every square gives us three crucial pieces of information. First, a chemical letter symbol, like H for hydrogen or C for carbon. Second, a top number, called the atomic number. This is the absolute identity of the element, because it tells you exactly how many protons are in its nucleus. Hydrogen always has one proton, helium always has two. And third, you're going to see a bottom decimal value, which represents the element's average atomic weight or mass in its natural state here on Earth. Now, you might be wondering, why is that bottom number a decimal and not a clean whole number? Protons and neutrons are whole things, right? Well, that mass is an average because of something called isotopes. Isotopes are just different natural versions of the exact same element. They have the same atomic number, the same number of protons, but a different number of neutrons, which naturally changes their weight. So for carbon, which always has 6 protons, there's carbon 12, carbon 13, and carbon 14. So, if you look at carbon on the periodic table, the average atomic mass is 12.01. It's incredibly close to just plain 12. Why? Because a staggering 99% of all carbon atoms on planet Earth are specifically that carbon-12 isotope. The heavier carbon 13 and 14 are so rare that they barely pull that average up at all. This decimal is actually super helpful because it tells you instantly which isotope is the most abundant in nature. Finally, Section 5. Elements in daily life. To truly master this map, we need to step out of the abstract for a second and see how these symbols translate directly into our everyday physical reality. Because the periodic table isn't just stuck in textbooks, it is quite literally everything you interact with. Let's start with the invisible stuff. Every single breath you take right now is dominated by diatomic elements from the right side of our map. The air filling your lungs is roughly 79% nitrogen gas, and about 20% oxygen gas, and both of these naturally exist as molecules composed of 2 atoms paired together. Let's rapidly fire through some other familiar landmarks on our map. Lithium, that highly reactive group 1 metal, is exactly what powers your smartphone batteries. Fluorine, the aggressive non-metal halogen, is found in your toothpaste as fluoride to protect your teeth. Calcium, an alkaline earth metal, strengthens your bones. Silicon, or temperature-sensitive metalloid, is the core foundation for building solar cells. Lead, known weirdly as PB on the table, powers heavy car batteries. And radon, a noble gas that comes from the breakdown of radioactive materials in the ground, can quietly and dangerously seep into unventilated basements, making it a real serious health hazard if you don't open your windows. So, you see, the periodic table isn't just some boring chart to be memorized. It is a master blueprint of our entire universe, organized with just astonishing elegance. Every metal that conducts our electricity, every gas we breathe, and every mineral in our own bodies has an exact coordinate on this map. Now that you hold the keys to decode the universe's building blocks, which hidden elemental coordinates will you be able to identify the next time you look at the world around you? Keep your eyes open, and thanks so much for joining me on this explainer.